I'm going to talk about consensus broadly, and then we're going to get into the details. But the reason that I'll start with just consensus is that I think it's easier when you understand Simplex, which is sort of the primitive that is the simplest version of Alpenglow you can do. And if you understand that, you can really start to understand how to make multiple concurrent proposers after that by just putting the pieces together. And so I think it'll be, we'll spend about half the time just talking about consensus topics in general. And then once we get to, a consensus thing that is like basically a simpler version of Alpenglow, we're going to be able to put it together very quickly and get a multi-proposer thing out. So what is consensus? It's basically the science of getting a bunch of potentially Byzantine computers around the world to agree on something, and not just anything, but for us, our purpose, we want them to agree on this thing that we call the log, which is an ordered sequence of transactions. And it's append only, and we're going to put some additional properties on it that you may have heard of before. One of them is safety, which means that once we add a transaction to the final log, there's never any conflicting finalization or like basically forking or this kind of behavior that would basically be a violation of the append only property of the log. And then liveness means that this thing keeps on growing even when a leader crashes or misbehaves or messages stop arriving. And we have some specific models that we like to use. In fact, there's a whole spectrum of them, but these are the three that you first learn when you start talking about consensus. We have synchrony, which is that every message arrives within some fixed bound delta. And delta is something you probably will hear a lot. It's also sometimes called the global network delay. The way to think about it is like if you have a node in Tokyo and you have a node in New York, you have to send the message across the fiber optic cable, and that takes some amount of time. I think light travels through fiber at some fraction of the speed. I think it's about 0.4 of the speed of light through fiber optic cable. And so the round trip New York City to Tokyo is around 100 milliseconds. And so you're often going to think of delta as being around 100 milliseconds. Or I think in this case, I have some nodes in Singapore in the clusters and some nodes in like Miami. And so it's actually more like 125 milliseconds. So synchrony is this very strong assumption, which of course is not true. Like it's not true that when you send a packet from New York to Singapore, it arrives 100% of the time within 125 milliseconds, right? So we have these other models of states of the world. One of them is asynchrony, which is that every packet eventually arrives. So maybe you're using TCP and like you just like keep trying to request the thing if it didn't succeed until you get the ACK, but it might take an unbounded amount of time. So this is a very like conservative assumption about the network, and it doesn't make very much of a statement. It just says, if you try to send me a message, like I will eventually get the message, but it could be in 1 day, it could be in 10 years, it could be in 125 milliseconds. And then there's this mixture of the two because asynchrony turns out to be very hard to do consensus in. So we have a bunch of like nasty impossibility results there, which is called partial synchrony. And partial synchrony is we're in an asynchronous period in general, but after some global stabilization time, GST, which we don't know when that global stabilization time will be, but it's at some point in the future. After that GST, we enter a period of synchrony. The final thing in our model is the adversary. And we're going to use the simplest, most common one for Byzantine consensus, which is that we have 3f plus 1 nodes. So n is equal to 3f plus 1. And in this case, I have a cluster that has 10 nodes. So at most 3 can be Byzantine. And Byzantine just means they can do whatever they want. They can double sign, they can stop sending messages, they can send more messages than they need to. They can disobey the rules of the protocol arbitrarily. And importantly, they're all controlled by the same adversary. So there's a bunch of details about how we model these mathematically. But the key is these guys can collude together and coordinate. So that makes them more powerful. If you have like an adversary who, this is a more realistic model, right? If somebody has 33% of the stake, then they're going to run the same exact attack on all of them. And they'll be able to coordinate however they want before the attack starts. So this is actually like a pretty strong adversary. They can do a lot here. And so we need to be pretty careful about how we design these systems so that we don't violate safety and liveness. So I'm going to go over this protocol called Simplex, which came out in 2023. It's kind of similar to Tendermint that came out in 2014, but has like this one key difference, which makes it faster. In the normal case, we have a leader. One leader proposes the block, and he sends that block out to everyone. That's these white arrows here. So that would be Turbine, would be sending the block out to everyone. And if that block arrives before a deadline, then we produce a notarized vote. And we produce a notarized vote, and we send that to everyone. Once everyone has 2F plus 1 notarized votes, that's called a notarized certificate, and we send that to everyone with a signature on top of it. So a signature on top of 2F plus 1 signatures becomes a finalization vote, and then aggregating those signatures together, 2F plus 1 finalization votes becomes a finalization certificate, and that means the block is final. A basic idea of this is if 2F plus 1 voted to finalize on top of a notarization certificate, and it's the same notarization certificate, then at least F plus 1 of those nodes are honest, not Byzantine. So they've seen the notarized certificate in the block and voted to finalize it, and therefore they will not they know about that thing, and the notarized and the finalized certificate has been formed, so they can never vote for a competing notarized certificate in that block. And in the Tendermint language, this is kind of called the lock. So the first stage of voting is we're locking that we're only considering this one block, and the second stage of voting is to confirm the locked block. And the reason that we have to do that is because a malicious Byzantine validator could sign more than one vote. So that's what happens when everything goes right. If the proposer misses the deadline for some reason, like he sends his block too late, or he forgets to send it, he goes offline, or the network delays him so he just doesn't arrive in time, then the key innovation of Simplex over Tendermint is that we have this new idea called the skip vote. And that's what these X's are representing here. So we'll vote skip, and then 2F plus 1 skip votes can be combined together to form a skip certificate. And that allows us to move on to the next view. So these are the two most common things that you'll see. And then there's this weird thing that only happens when we're not in a synchrony world, which is, so this can happen before GST, but not after, which is that we are in a world where we didn't finalize or skip. And that might happen because basically this happens because of network delay mostly. And if that happens, the next view will pick up the notarized certificate or the skip certificate and continue the chain on. Okay, let's, so this spinny globe is not just a visual aid here. it's actually going to be an animation for us to see a live run of the protocols that we're going to look at today.
This is where you burned all your credits.
This is where Mythos. Yeah, this is where I ran out of Mythos credits. So these are running on our invalidator cluster 1. We have 3 invalidator clusters. This one is 10 nodes, and this is the first cluster that Alpenglow ran on. We have another one that's 45 nodes. That's also geo-distributed, but that one actually gets used for like real stuff and not demo, so I couldn't use that one, unfortunately. That one's testing a bunch of invalidator tests on Alpenglow right now. So we got to use the baby one. And all of these are going to be, we're going to have a timeline that's going to show up. Let's get into it. Okay, this is Simplex. All these white messages are votes going back and forth. And let's zoom into the timeline here. Whoops. Let me slow things down a little bit. So here's your proposal. And then you can see he proposed and then he notarized, and the other 2 Singapore validators also saw it very quickly after and cast their notarized vote. Then this Tokyo validator and this Tokyo validator saw it later. This London validator saw it quite a bit later, and I think the latest validator to see it was probably down here in Miami or Houston or Dallas. So the idea is, like, we proposed, we cast our notarized votes, then everybody saw their notarized certificate. Once they saw their notarized certificate, they cast their finalized votes, and then we finalized the block. So this is answering the question that was asked earlier, which is, do we have a hard deadline? So there's this idea of responsiveness. Alpenglow is a responsive protocol, and the marketing for this is that it proceeds as fast as the network allows. So as soon as a prior block is locked in, the next leader can build on top of that block, which sounds really good. And in the historical world, they used to just like parameterize these things so loosely that once you added responsiveness, it took the protocol down from like, you know, a 1 second slot time to a 400 millisecond slot time, because there was just no reason it was actually set at 1 second. Or so responsiveness was kind of like a way to get around the fact that they were actually setting overly conservative timings. What we observe now, and there's a new growing thrust in the literature, which is talking about these non-responsive protocols. The argument they make is actually a timing games argument, which is that the validator can propose as late as he wants, and it's in his self-interest to propose as late as he can. So he's going to propose all the way up to the deadline. And then we're sort of back at the fixed view schedule with an aggressive fixed view parameterization. So that's the argument that the responsive protocol haters would make. I think it's, as an economist, mostly, I'm not like a consensus researcher primarily. I'm an economist, so like I think of things as rational validators, and I am much more in the non-responsive camp. And one thing we observe, like I didn't realize until I just started running some experiments, is the clock sync protocols are actually very accurate. Every protocol you're going to see today is a non-responsive protocol, and everything, all the cluster, 10 nodes on the cluster, the accuracy of clock sync across those nodes is within 1 millisecond. So we're working at 50 millisecond timescales at the least. And so within 1 millisecond of clock accuracy across these nodes is perfectly accurate. And this is something that was not a it has only recently been discovered that you can do Byzantine clock sync and get very accurate timestamps across nodes in practice. And
yeah, because wasn't there a big debate that wasn't possible because different clock timings across different mediums of measuring time? There was a lot of debate that it wasn't even possible, right?
yeah, there was like a huge debate, and then you just sort of like actually run it, and it just works. I don't know if we needed 10 years of debate, but all of the protocols were built by theorists. The theorists had some theorem saying that this thing was not possible, and then the people who like actually worked on it were like, well, we did it and it's working. So I don't know what to tell you. Yeah, so that's sort of the world, and there's a series of 3 articles on this blog called Decentralized Thoughts, which is a great, very accessible consensus blog. And it goes over the arguments for and against, and a bunch of protocols, modifying some of the bits and the details to get these fixed view schedules to work. In the Constellation paper, the thing we have is actually a hybrid of the two, but we still require the synchronized clocks anyway. However, we are not reliant on synchronized clocks for liveness or safety. So we use the synchronized clocks for the economic guarantees, and we don't use them for the safety and liveness guarantees, because we didn't want to change Alpenglow if we didn't have to, right? So basically, we want to build something on top of Alpenglow. Yeah, so from an economist perspective, I'm like very bullish on synchronized slots. I think there are a bunch of reasons that the code is cleaner when you don't have these synchronized slots, because you have a purely event-driven system. But yeah, I don't really buy into it. So that's my opinion. I think the research team has a slightly different view than me. So that's just my disclaimer that this is opinions of my own, not Anza's. So another ingredient, and we're going to get into some of the more complex protocols, is this thing called asynchronous execution. On Solana, we like to call it bankless leader. It has some kind of like a dirty reputation among the devs for some reason, but plenty of protocols already do this. Sui, Aptos, Monad, Tempo has it. Arc is going to have it. It's basically just delaying one slot to put the bank hash in. And I don't think it's super scary. The reason it's controversial is related to how well we can time the execution of the blocks. So it's like execution issue, not a consensus issue. So yeah, I won't discuss too much of the debate around that, but it's basically the debate around, do we remove the CU cap or not? Because removing the CU cap on the block is nice. We get infinite block space, right? In theory. But it doesn't, it's not compatible with asynchronous execution, and asynchronous execution allows us to do a lot of cool things, which you're about to see. And yeah, again, it kind of requires like accuracy in the CU metering. And the way this works is we have to do a few changes on which checks we do. We currently check based on the active bank state, and we need to change those to be not dynamic based on the bank state. This is for fee payer check and stuff like that. And then the other thing we would do is we would move the bank hash from the current block to, say, the previous block. On Monad, I think it's 3 blocks delayed. And I think the same is true on Sui. Okay, so we have this asynchronous execution. Now we can do another thing, which is instead of replaying transactions in the order that they're received or in the order that they were packed by the leader, we can reorder them however we want. If we have 3 blocks from 3 different leaders, we can smush them all together by just concatenating them, and then we can order them, say, by priority fee, and then execute them in that order. because now that we've decoupled the two, there's no reason that we need to execute in the same order that the leader proposed the block in. I'm simplifying a little bit. There's a little bit of detail on the parallel execution side. All of those details are in the Constellation paper. So it's not just bubble sort, right? We have a basically a scheduler that has to run inside the sort by fee simplification here, and that scheduler is more complex than bubble sort. Obviously, it takes into account with transaction conflicts. Okay, so here's a paper that I'm gonna announce on Twitter today. It's just posted on Archive. Gatling is not a multiple concurrent proposer protocol, but it's like sort of a good way to ease you into this idea of async execution and what it enables and what we can do with just very simple primitives stacked on top of each other. So each of these, pi1, pi2, pi3, pi4, are their own version of a simplex consensus chain. And when we think about the execution log, we're going to try and run these things independently for consensus. They're not referencing each other with like parent references, pointers, or anything like that. But when we do the execution log, we're going to merge them together. And here we're not even going to do the merge rule. We're just going to execute the block in the order that the leader packed it for us. But what this allows us to do is basically go to slot times that are epsilon small. So like 10 millisecond slot times with leaders rotating every 10 milliseconds. What you're about to see, I forgot the parameterization. This is it running right now. You can see it's very active relative to ordinary simplex. And I will need to zoom in a little bit and slow this thing down. Too many things on here. Yeah, okay. This is all timeline view. And these are all the proposals. And you can see these are happening. This one is one every 100 milliseconds. But there's no reason that it has to stop there. In fact, I tested one where we had 50 instances, which I think is a 5 millisecond block time on here, and it was working fine. So we can basically go to arbitrarily low slot times, and we can, as you can see, we're still rotating the leader here. Let me go back to real time here. The leaders are rotating this fast compared to we rotate leader every 1.6 seconds right now.
Yeah. Well, thanks for awesome presentation overall. Just two small questions. Is like with the slower time frames, and you've tested, and it has the potential to be done. So do we have a like smaller, like more fair market and less like attack surface? Because it used to be like more fair closing and earlier, so we don't have to like. There is probably no need for much of a like abstract schedulers which are currently present to make it more efficient, because it's in a smaller time frames. It's already sitting there. And the second short one is like I just saw the sigma, so this is like standard deviation of the deltas, so it could evaluate through the time, because like with better latencies we'll have a slower sigmas, so it will be also changing.
Yeah, good question. Let me answer the second one first. So the sigma is the standard deviation of let me be very precise, because I don't want to say the standard deviation of delta, because delta is a parameter that is not a random variable, so it can't have a standard, or it has a standard deviation of 0. But the thing you're saying is, I send a message from New York to Tokyo. What is my jitter, right? And the lower the jitter, the tighter you can set the timings. Is that what you're saying, basically?
Yeah, exactly.
And that's obviously true. In this cluster, I think we have like some pretty good DevOps people. So the jitter was less than 1 millisecond on all of the connections that I tested. But that's not true in mainnet. So we have to be a little bit more conservative. But I didn't set the timings particularly aggressively here. Like right now, the inter-proposal time on each instance, 500 milliseconds, could easily be down to 350 milliseconds, I think, even on this cluster, which is pretty geo-distributed. This cluster is more geo-distributed than mainnet right now. Mainnet is like 70% in Europe. This one is 60% in Asia, but turns out the difference between 60% and 70% is very big when you need 70% to finalize the block. Let me talk about some MCP. Also, this is like kind of orthogonal to MCP, by the way. Like we could just do this and MCP as long as we're willing to tolerate even more white dots flying around. So Braid is one of my first proto MCP designs that I came up with. It's very similar to Gatling. With Gatling, we had the offsets. With Braid, we don't have the offsets. And then we're gonna add that merge rule logic in to figure out what the final block that we execute is. And if somebody doesn't get their, if a block gets skipped, then we'll just have 3 of the 4 that we confirm. Okay. So you can see we have, it's the same number of packets as Gatling, but they're like very bursty right now. And you can see like, let me remove all the clutter. Is this right? Okay, there we go. So this is the proposals. You can see there's 5 proposals. There's we're doing here one of these rounds every 500 milliseconds. You can imagine we could just easily, if we have the bandwidth, we can just combine this with Gatling, and we could have both approaches, and we could have arbitrarily low slot times with multiple concurrent proposers, down to, you know, if we have 1 millisecond of clock sync issues, you know, we maybe can't go down to 1 millisecond, but we can go arbitrarily low that way. Okay, so that's one proposal, and I think you can start to see just intuitively, like there's a lot of messages flying around here. Are there a few ways we could do this without all of the messages flying around? Also, I will say that most of these are all, you're looking at the happy path, right? So these protocols, when you have more instances in flight, you can have problems. And I'm not really going to talk about them today, but they're in the papers. And so you have like more stuff in flight, you have head of line blocking, same things you would have with, you know, asynchronous programming, you have with asynchronous consensus with multiple instances going at the same time. Like if I'm running 5 instances and there's something wrong with one of the instances, I'm going at the pace of the slowest instance. So we need to be really dialed in terms of our implementations and the way that we do things, and make sure that not just like one chain is not progressing at a slow pace for some reason because we messed up. So the margin for error gets lower because we have any error is 5 times more likely to. I have 2 more for you. This one we call MinCP, and we think it's the simplest possible version that we can come up with. Obviously, like there are reasons that simplicity isn't always the number one thing, but let me describe how it works. Normally, we vote on 1 block at a time. Simplest thing would be, let's sign all the blocks that we received before the deadline. And if we all saw the same set of blocks, then we will finalize. And if we saw a different set of blocks, then we'll skip. Yeah, so the idea of this one is instead of voting on one block at a time, we're going to vote on the vector. And this is the first thing we came up with, obviously. It's not a bad idea. It's just that if one proposer proposes late and splits the view, the whole thing skips. So this is not something that can scale up to, say, 16 proposers, because our liveness would be basically any Byzantine proposer out of the 16 could cause the slot to be skipped. It's this question. CPU cache line, I would say the biggest advantage of this approach is that it is very simple to do. It does not require consensus changes whatsoever, except for this like change that we're assigning, we're assigning this vector of block IDs instead of one block ID. And so the consensus side of the change is very simple. That's the biggest advantage of this. And it doesn't introduce a bunch of extra vote traffic.
Yeah, so the decision to go to the vectors is actually because of the it's quicker to do by SIMDs, and probably because everything is vectorized, so it adds on hardware performance advantage.
Maybe I should not use the word vector. Maybe vector is confusing, but because I'm using it in the mathematical sense of this is just a bunch of things but I would say that the vectorization probably does not have a big performance implication on what's going on inside the validator. It's more of what happens in the messages that are sent back and forth where this approach is nice. Does that make sense?
Thanks. Yeah, thanks also.
Okay, let's see this one.
Quick question, if you don't mind,
Go for it.
for that part. So we were thinking with the guys about attack vectors or attack surfaces for this new consensus yesterday. And we did the research quite some time ago, and we noticed that 500 of the top validators are using some kind of modification on their client. And of course, the timely vote credits popped in because they were delaying some votes on the blocks. Do you see any kind of attack surface with these 16 proposers that, for example, probably not, vote delaying or voting later or proposing later, but basically just trying to censor some leaders in the chain, so when they are getting to the point that they have to have blocks proposed, then accidentally some of the proposers or most of the proposers decide not to send the proposal on time? Would that happen?
Yeah, there's a number of things that could happen here. So I think there's probably multiple things mentioned, but let me take them one by one. So one thing I might do if I'm a rational proposer is I still want to wait as long as possible to release my block. And so I kind of creep up to the deadline, and occasionally I am too late. And when I'm too late, I split the view and everybody's block gets skipped. So that's one issue with this particular MinCP approach. We're using here the timeliness committee for whether the block arrived in time is the validator set itself. And so the validator set is sort of doing a dual purpose, which is saying, I'm going to enforce timeliness and I'm going to do consensus. With Constellation, which you're about to see, we have a special role whose job is to enforce the timeliness. That's the attester. And so if you push up to the deadline in Constellation and you try to split the view, it doesn't work. So that's why Constellation is basically designed the way it is because of the attacks that you mentioned. Did that answer all the questions, or were there other ones that I didn't cover?
No, that basically answered the question on these attack surface, certainly. So good that you guys already thought about that. Even though that with timely vote credits, we know that validators maxing out the time before they vote, even in the current system. So they probably gonna max out there as well.
Yeah. I mean, it's heavily for the voting behavior itself. It's very heavily dependent on the actual vote credit economics. So if the vote credit economics are changed, then that the bad incentives can go away. Also, on the other point, which is like, what if you just didn't vote for a particular proposer's block, right? So on that point, we have this assumption, which is that no more than F of the 3F+1 guys are Byzantine. So not voting for a particular node just because we don't like him as Byzantine behavior. This is not very satisfying, but from an academic perspective, it's like we're working in this model where our system can be double spent if more than F people decide they don't want to run the code. And so it's almost not worth thinking about other kinds of attacks, because like if you had 3F+1 of the, or if you had F+1, you could literally double spend. So that is the classical academic answer. Now, I don't know if that's super correct. Like, I don't know if that model of the world is correct in that even if you controlled F+1 voting behavior, maybe it's harder to convince people to do a double spend attack than it is to convince them simply to censor a particular proposer. But that's the classic like academic answer is like, we have this assumption, and the attack that you're describing would be a violation of the assumption, so it's not considered in our model. Does that make sense?
Yeah, perfect. Thank you. Be closely gonna watch all the pieces, what's happening for sure.
Yeah. We try to project everything in our models, but obviously we will not be always able to do that. Yeah, so just here's the basic idea, which is that we are gonna propose, then we notarize vote, then we do our, where are these notarized certificates? Then we get our notarization. And then we do our finalization. That's the basic. Why is this? I think some stuff is overlapping. Anyway, these are the proposals. You can see there's multiple proposals per slot, just 2 for the sake of this demo. But you know, this thing is very simple. It's very easy to do. It works. Ironically, it's the one that I had the hardest time getting to work for the demo for some reason, but here it is working. Very, very boring one. Last one for you guys. And I have one more bonus topic. So you guys already went through the paper, is that right?
Yeah, we've went through it. A lot of people have been studying it. Some people in the class have even broken some of it down on X. So this is awesome to get into the weeds here.
Okay, cool. Yeah, so I don't have too much to say beyond what's in the paper, but I do have the demo for you guys. But just while we're on this topic, like the attestation committee here is the same as the current role of the turbine root. So it's not like it looks like it's introducing a new network hop, but we already proposed through a committee that looks like the attestation committee. We're just kind of renaming that turbine root to attester and giving him an additional job to send the attestations to the consensus leader. So he's still doing his job as the turbine root, and we're not necessarily adding an additional hop there. The real hop that we're adding is proposer to consensus leader. Like that's the extra activity, because the consensus payload, we haven't done this yet, but I suspect that the consensus payload can be turned into a very compact format, because all it is these attestations, and they can be compacted very well, and then it may fit even inside a single packet, and then we're going to bypass Turbine with it eventually. So right now it's an extra Turbine round, but in the future it will be just one extra round, which is like, I would say a Turbine round is like 1.5 delta, and a regular round is just delta. Okay, let's get into this sim here. Okay, these are the proposals. I have 2 here, but in principle we can go, I could have had all 10 of these guys proposing, to be honest. And those proposals are sent to the attesters. And you can see like the clock sync here, right? Look at the attestations. This is like the cleanest line you've seen. You can see the attestations are just like right on the money of and a great timeliness committee. And then that's the clock sync that we talked about. Now we send to the leader, and the leader builds their block, and they send it out. We need to get some notarized votes. Eventually we'll get some notarized certificates, and then we will finalize. And how often are we doing this here? I think we're at something like 500 millisecond cadence. Is that right? Let's see. Yeah, we're at like a 500 millisecond cadence, or I think 450 millisecond cadence here. And you can see the traffic is much lower than we saw in Braid or Gatling, because we're not doing separate consensus instances. And you might ask, does that traffic from the consensus matter? Sort of. If you try to do like Gatling with 10 concurrent proposers and every 5 milliseconds, you're probably looking at more network bandwidth than we have in total. So then we don't have very much room for transactions because we're using it all in votes, which is not a great spot. But if you're sort of reasonably parameterized, maybe once every 50 milliseconds, we have 5 proposals. Once every 50 milliseconds, we have 8 proposals. That's doable. The Helios validator runs 100 gigabit NIC on mainnet right now. So they're available. And a lot of the existing bandwidth limitations that we have are not necessarily based on the NICs themselves, but based on how much stake certain validators have, because they're so often participating in Turbine and their bandwidth is proportional to their stake. So one way right now to get like a cheap like 3x reduction in, or 3x increase in the amount of available bandwidth we have for blocks would be to go to all the big validators and say, can you split up your stake into like 3 different validators with 1% stake instead? And we would immediately achieve a 3x increase in the maximum size of the block that we could transmit. So there's a lot of stuff we can do in terms of bandwidth overhead, and just bandwidth has like this insane scaling law, which is similar to Moore's law. But I think the exponential is like slightly slower, but this thing is doubling every 18 months or something. So I think bandwidth is not as much of an issue as people think it is. I come from Ethereum land, and they always are talking about the solo staker with like 10 gigabit or 10 megabit upload speeds, 5 megabit upload speeds. And I was reviewing one of my old posts on ETH Research this morning just to prepare something, and it was about setting the bandwidth requirements for the ETH nodes. And somebody commented on the post, they were like, oh, like I live in Las Vegas and I only have 5 megabit uploads, so therefore like these numbers are too high. And I was proposing 50 megabit upload download node requirements for Ethereum. And yeah, obviously we have 100 gigabit nodes on Solana now, which is kind of good. I don't like to be artificially constrained by that stuff anymore. Any questions on this? I have one more topic. Go for it.
Yeah, so if the bandwidth isn't an issue, so can we just fantasize about the future where we can use something like Starlinks or more distributed systems and maybe have a better network topology, which will be the trade-off. So we'll have a better latency because of the topology compared to the bandwidth.
Yeah, ultimately, this is kind of an economic question. You can run a node in South Africa today on Solana if you want to. It's just that you're going to lose a bunch of proposal time.
Yeah.
So we thought about this a bit. With multiple proposers, you kind of want to be at a different spot in the world than other people because you get transaction volume that other people don't get because you're closer to them. So what I expect is with a multiple concurrent proposer system, we will have a lot of nodes in Europe. We'll have some nodes in New York. We'll have some nodes in Tokyo. I don't know how many transactions we actually get from South Africa. So I don't think we're actually going to have a lot of people in South Africa from an economic perspective until there's a bunch of demand. And if there is demand, suddenly the Johannesburg Stock Exchange becomes the #1 global exchange, or maybe there's some new unobtainium discovered in Cape Town. Maybe then we're going to be trading in South Africa, and the validators can easily just move over. But I see geographic decentralization less of a technical problem, more of a economic problem. Okay, so this is this new research that came out from SAY, and it's basically a thing that we thought about in a slightly different form, which is we talk about getting censorship. We've also talked at times about achieving hiding. One thing you might want to do is protect yourself from getting sandwiched by the users. And there's two parts of that. There's hiding within the consensus, which is a lot of what we've done with the original multiple concurrent proposers paper with Supernova, which is about achieving privacy until valency, which is when consensus resolves. And then there's this other side of the coin, which is between the user and the proposer, do we have privacy? There's a few ways to do that. One of them is we put the validator in a TE, and we encrypt it to the TE key, and then he sends it off. But another way, I always found TE very unsatisfying because it's kind of like a cheat code, and also they're not very secure. So I always found it to be unsatisfying. So another way to do it would be you use this kind of hiding erasure code. You take your transaction, you shard it into several pieces with something like Reed Solomon and an all or nothing transform. So what that means is only if you have 2 of the 3 pieces can you reveal the transaction. So then you submit that to each of the proposers. No proposer has enough pieces to see your transaction until we go to replay. And at replay, we combine them and decode them and execute them. And so that way, now if we do the threshold encryption that we talk about in Supernova, and we do this thing, your transaction is encrypted all the way from when you submit it to the time it executes. And there's nobody who can see it in between. So that's sort of future direction. And yeah, the SAY team is actually really good, and I enjoy reading what they put out. There's actually a lot of similar thinking going on at a lot of the different blockchain frontier labs right now. So it's kind of a cool time to be working in blockchain research. So this question, interesting to hear how the consensus discussions and confirmation happened, is that there could be two things that's about. One of them could be the social consensus, and one of them could be the actual consensus. What's the...
Oh, it's more about you know, the story behind how actually it happens when there is like chain does change, and the world of like development, the world of like everybody affected. So it's very interesting how this discussion happens, how we took in consideration how like you know, security issues are taken into the account, and how the story went is like, you know, more of a, I'm not a journalist, but very similar kind of question. Is just generally it's very interesting how it happens.
This is by far the hardest part of my job. And so everything you just saw is like the fun part of my job. And then the building. So building consensus algorithms is what I like to do. Building consensus among people is what I have to do. And it's actually where I spend a lot of time. And there's a lot of constituents on these chains. And it goes all the way back to something like the block wars. I just wrote an article on Twitter about the history of the block size wars on Bitcoin. Bitcoin had a 1 megabyte block limit that Satoshi added. And when he added it, somebody was like, what if we need to change it later? And I read the response that he put on Bitcoin Talk. It sounds exactly like Tolly, because he's just like, oh, we'll just update it. Like, if we need to change it later, we'll just update it. We'll have a schedule. We'll do this. It kind of sounds like Tolly to me. And then 5 years later, they were starting to get like half full, and then people were like, wait, we actually really need to increase the 1 megabit or 1 megabyte block limit because we're running out of space in Bitcoin. And if we want to be electronic cash, then we need to be able to serve. There's a post that says like, we should be at least able to serve as much capacity as PayPal does. Otherwise, like, what are we doing here? And all the miners agreed with this, but the Bitcoin Core devs did not agree. And this caused a lot of basically back and forth. There was a client called Bitcoin XP. That client got to 10%. Then there was a series of compromises, Hong Kong compromise, New York agreement. And eventually in 2017, they gave up, basically. Like, they were just trying and trying and trying, and the Bitcoin Core devs refused to implement in Core. And 80% of the hash power was behind this agreement. And they had a new client called BTC1 that was supposed to have, the only change was this 2x the block size limit. And they couldn't get it in. Like, they couldn't get it in. And that upgrade was scheduled for November 8th of 2017. In December of 2017, Bitcoin block fees per transaction hit $50. And in December, Steam turned off Bitcoin payments for their store, and Stripe turned off Bitcoin payments. So it's been going on for a while, I would say. But luckily, we're in Solana. We're a lot less ossified than, and I think we just have more of a culture of like wanting to get shit done. And so, yeah, it's definitely not easy. Like, there's people with businesses that are building, that are building block producers, and like those businesses are getting disrupted by this change if it goes in, right? So, but at the end of the day, I think everybody wants Solana to win, and like we need to make progress. So we're gonna get it done.
If I have a small just question, it's like the only worry I have is about like you know, we will get faster transactions, and it's all about speed and competition. I've been annoying a lot of people with your question recently, and I would like to hear your take shortly. What happened with the HFT world and the stock exchanges is like he went into the nanoseconds colos with 100 gigabit bandwidth and stuff, and at some point it will disrupt the system itself. But because those people are bringing a lot of value and money into the you know, stock exchanges, so a lot of discretionary traders and like algo or like NFTs, they just left the market. Or the thing which happens to the German stock exchange, there was like HFTs sending like false orders and then coming, getting them back, breaking the market microstructure and creating some kind of noise. Which actually at some point, I personally knew a lot of like traders who've been trading discretionary on their own accounts or for the company accounts, for the small prop firms. They've been just leaving the market because like, oh, we can compete with that, and also the stuff happening. So I actually see Solana as a great place for those traders to come in, to join and to trade and have the volumes and also have the the new products, because they're really always inventing the stuff since the 70s or 60s. When taking this consensus into consideration, what I was thinking is like the smaller block times is actually the way to solution. But how it's like what are the talks and ideas towards this one? So are we aware? Are we ready for this kind of happening? Because we see a lot of like faster transaction happening. So I was actually like even recently was discussing some kind of anti-cheat on the kernel level, what Vanguard is actually doing for the gaming. So they tracking what actually the nodes are doing, but it's like because it's an open source and because it's a different mindset to the gaming, to the proprietary software. So it's like a little bit hard to do, but maybe some kind of auto metrics or some kind of metrics could be revealing, and maybe slashing, or rather allowing to make better profit for the operators who are fair.
Yeah, I would say the whole goal of these types of changes is just slowly like whittle away at all of the attack surface that exists for people to mess with the HFT activity. And I think like we already have validators who are like reasonably well behaved, and you can see that things are sort of working, and people are sending quite a few Oracle updates, and the system is not going to look exactly the same way as TradFi because it just can't, right? We have to wait 300 milliseconds to see the result. All of the activity has to live inside the virtual machine, and that basically means that you have on-chain collocation. Anyway, I have like 5 hours of answers to this question, but my basic response is, we're working on it. That is exactly why we are working on these types of changes.